This exhibit has to do with bonding, primarily bonding and grounding. And I don't know how much you guys have seen or know about all of that. What I was going to show you here is a little bit about how to test your bonding system, and a little bit about why you want to do that. Concrete is conductive electrically, and so if I take advantage of the fact that I've got steel in it, which is also conductive, then I can build a system which reduces the amount of current that can get in the water, which is obviously what you want. That's where all of these events have occurred, has been in the pool. But in terms of the code stuff too, we've shown the alternate means for bonding the perimeter, which is this number 8 wire. I don't recall that, I think on the original exhibit we had, well, it was right here. We were going to show bonding in the deck as being the primary means, but they didn't get that on there. So this is something that never gets thought about once it gets put in the ground, if it gets put in the ground. It did not exist as a practical matter before the 1970s. And even if it's in the 1970s, that's what now, 40 years ago? 45 years ago? And we're asking for stuff to stay in the ground and stay intact for 45 years when they really didn't know how to do it at the beginning. So you've got a lot of pools out there that are not bonded, or the bonding has deteriorated to the point that it's really not functional. And there's a way to test it that's very easy. The only thing unique about it is that if you don't have one of these or something equivalent, then it's going to become a lot harder for you to do it. Because believe it or not, there are some advantages to the old-fashioned analog meters. It has 3 advantages to it compared to the nice, sexy digital meter that everybody uses, which really help in terms of testing bonding. The first one is when you're testing bonding, you're usually looking at long runs of wire and wire that's in the dirt, where you may have situations where the wire or connection is separated and you're trying to push current through dirt. The nice thing about this meter, or this type of meter, is it usually has like a D-cell battery in it, rather than a little 9-volt transistor radio battery, which really doesn't have enough oomph to push the current through. And so it can give you bad readings. The other thing that it can do is you'll notice over here on this little knob there's a plus DC and a minus DC. So when I'm testing resistance, I can actually reverse the polarity of the meter. The big advantage to this is obviously this thing's got, I've got 6-foot test leads on this thing. Right, when you're out of pool, that's not going to help you a whole lot. Right, you're typically, one of these is going to be a 6-footer, and the other one is going to probably be up to 250 feet. We've had situations where we've had to go over 500 feet on large aquatic facilities. Right, the thing that a meter like this has that a lot of the new ones doesn't is this knob over here on the left, which is 0 ohms. And you'll notice I can tweak the needle with that. And when I do that, right now it's reading 0. The only place it's reading 0 is between these 2 clips. Right? It has made these leads completely transparent. So if you've got 250 feet of wire on there, you can zero that out so that the amount of resistance that you're measuring is exactly the amount between these 2 points. Right? The way you want to do this, if you want to come over here, this is not rocket science. If you've got a metallic light that's grounded, come in here to the J box and disconnect your ground. Right, make sure the power's off before you do any of this. Right, lock it out, tag it out. And you want to clip one of your leads on that ground wire going to the light. Now, what this meter is going to do, in the most physical sense, is that battery is going to inject current into this circuit. And what you're actually reading on this dial is amps. But the dial's been calibrated in ohms. That's why if you look at this, if you look it up close, if you've never seen one, All the zeros are on this left-hand side, except ohms, which is over here on the right. And that's because the more current you're flowing, the lower the ohms. Right, the more conductive it is, the more the current flows. So we calibrate these, and so the resistance scale is backwards. If I zero that out, then I can make what amounts to a pretty accurate reading. All right, so I've got my long wire, however long it is, connected over there, and I come back over to the pool, and I look at all of the spots that are supposed to be bonded. Right, the most obvious one is right here on this screw, right on the light fixture. Everybody see that? This screw is the only piece of equipment in a pool that is consistently tested for proper bonding, because it's part of the UL test for the light. Is I'm injecting current that comes down the ground wire into this light fixture, comes out into the metal because that fixture is grounded, goes through that screw into the bonding system. And it's going to come out wherever I do the measurement over here. So I'm looking at the whole bonding system. And in this case, I've got two ladder pockets, so I can look at it, and you want to look at it, both of them. Right, if I've got two ladder, you want to look at both, because inevitably they'll only bond one. You'll notice that when I did that, the needle always went way back over to the right. Right? In testing hundreds of pools, what we found is that it turns out that the nice thing about this is there's no hair splitting that goes on. If you've got a good bond, it's usually less than an ohm, which is way over here on the far right. If you've got a bad bond, it's usually up 20 ohms, 30 ohms, 50, 70, right? There's a gigantic gulf in between these. If you've got a giant pool you're doing, you might see 2 ohms for a good one, just because of distances in the structure of the pool or whatever. But generally it's going to be less than an ohm, and you're going to get big numbers if it's a bad bond. So it's going to be pretty obvious to you if it's good or bad. Here's a bad one. I've intentionally, I realize you can't get to the bond beam in real life after the pool's built, but I'll talk to you about that again. But I've intentionally loosened this one, right? Look at what we're getting. See, it's floating all over the place. Okay, that's a bad bond, and we know it's a bad bond because I took it loose. There it is. There is a significant difference between bonding and grounding. Grounding is designed to provide a path for short-circuit currents. You have to size those conductors so that they can handle the maximum amount of current that can flow on a short circuit in that circuit, and it's designed, it goes back to the main panel, and it's intended to keep short circuit current high enough that a circuit breaker will trip, which is what you want, right? So it's equipment and fire protection. It's not personnel protection at all. Bonding is more in the line of personnel protection, right along with GFCIs. It's designed to try to keep the voltage levels spatially as close as you can practically keep them. So that if I'm standing here on the deck, for example, there's not enough voltage between my 2 feet that will injure me or kill me, right? Or if I'm in the water, so consequently, they're two different purposes, even though they interconnected a couple of